Believe it or not, we are on the last topic of the year, the ideal gas law. The ideal gas law is really applicable in any set of pressure and temperature conditions that really won't kill you. When you get a little drastic, really high temperatures, really high pressures, you do need to do another law called the Van der Waals or the real gas law. We're not going to deal with that. We're just going to see how you can relate everything about a gas together. Now remember, the combined gas law was close. It related pressure, temperature, and volume. Now we're also adding in the number of moles of gas. We're going to link that, we're going to include that, and that's going to give us all the information we need. You're not going to have to talk about one condition, change it to another condition, and balancing this and that, taking this measurement and that measurement. This is going to let you know all the different conditions in a given situation. And that's pretty cool. First off, let's talk about this little scenario here. Let's say I've got a hard-boiled egg and I stick it on the top of an Erlenmeyer flask. Well, how's this going to affect different things? Well, first of all, I take that flask and I dip it into liquid nitrogen. And let's see what's going to happen to a number of situations. The first question is, what happens to the number of gas moles? Well, a hard-boiled egg actually makes a pretty decent seal. So gas isn't going to go up or go down. It's going to stay the same. So it doesn't go anywhere. So far, so good. What about the temperature? Well, you've probably never felt liquid nitrogen. At least I'm assuming that. Otherwise, you probably wouldn't have a finger anymore, because the temperature goes way, way, way down. If a gas is so cold that it turns into liquid, pretty darn chilly. So that's going to go down. How about the volume of the trapped gas? Well, I know automatically you think, well, the temperature went down, so the volume has to go down. But remember, this is not a flexible container. It's a rigid glass container. It stays constant. So that means I just have to worry about what happens to the pressure. Well, I can talk about Gay-Lussac law to give me an answer to this one. If things cool down, remember what happened to Scuba Steve? If the volume doesn't change, the molecules aren't banging up against the wall as much as they were, so the pressure has to go down. So this is really the stuff we've covered so far. So what's this little bonus question? What's going to happen to the egg? We'll have to wait and see when we do this in person. But you can take a look at it for now and think about it for now. All right. This is the last section of the handout that I gave you. And these questions you should be able to answer by the time we're done with this situation. We're going to talk about the ideal gas law, what it actually is, formula that is, what the gas constant is, and the different numerical values of R. We're really going to be sticking with one, but this gives you an idea. Also in this case, we're just going to do kind of a true-false setup. So you should be able to answer these questions. And these are the four variables that can change, and you can rearrange them to do those solving. So we'll let you work on that together. But let's go back and just put these laws together. This is the idea of Boyle's law. Remember this, as the volume changes, it's going to affect the pressure and vice versa. Inversely proportional. So the pressure times the volume is equals to some constant called Boyle's constant for Boyle's law. Some number, didn't really go into what it was, no real need. Oops, went too far. Charles's law was this one. As temperature changes, if I keep the pressure the same, it's going to affect volume. So V over T equals some sort of a constant called Charles's constant. Again, we said the number was not going to change. That's why V1 over T1 equals V2 over T2. We just didn't go into what that number is. Gay-Lussac's law, same thing. Pressure over temperature is going to equal some constant. So even though we haven't mentioned them, we've given you three different constants, which could be a real pain. And that's one of the reasons we're going ahead with the ideal gas law. We also had a little added bonus, the idea of Avogadro's law. We talked about this a little bit, but here's a simple way to put this. If I put stuff in a bag, that bag is going to expand. Just like when I raise the temperature in a balloon, the balloon expands. So I can take a look at this as being, just like V over T equals some constant, V over N being the number of moles equals some constant. Likewise, if the thing doesn't expand and I have an increase in temperature, my pressure would go up. Now if I have an increase in the number of moles, the pressure goes up. put air in a tire, the pressure is going to go up. Makes sense. You just put more of these molecules in, it does the same sort of thing as if you raise the temperature. So that should give us another constant, Avogadro's constant, but that's a bit of a pain. So here's what we're going to do one last time. I put the n down at the bottom next to the temperature, and I just put it in with Gay-Lussac's law, but it could have been in either of them. And what this does is it lets me take Boyle's law, it lets me take Charles's law, and Gay-Lussac's and Avogadro's law stuck together. Now PV over NT, N being the number of moles, that is going to equal some sort of a constant. And this constant is the ideal, the universal gas constant. And that's what we're going to be using for the ideal gas law. You see I've got some numbers put in here. Let's see if you recall where these numbers came from. Remember, I told you that if you had a mole of a gas at 0 degrees Celsius, or 273 degrees Kelvin, and at 1 atmosphere of pressure, it meant I had to have had 1 mole of that gas. Or I could have said if I have 1 mole of gas at 273 Kelvin and 1 atmosphere, it takes up 22.4 liters. So that's all I've really done here. I've taken my number of moles, and that is N. I've taken the temperature of 273 Kelvin, and that is T. I've taken the volume of 22.4 liters, and that's V. And I've taken the pressure at 1 atmosphere, and that's P. They all have a place, and I can set an actual number, which means I can calculate a value of R based on these numbers that are right here in front of you. So you can literally calculate the constant. And the trouble with the constant is the units, but if I just take 22.4 and I divide it by 273, I'm going to get a value of 0.0821 liter atmospheres per Kelvin mole. I told you the units were a pain. But that is the universal gas constant. And that's what I can use to put together the ideal gas law. And this is the ideal gas law. Generally speaking, it's written this way. PV equals nRT. Remember, it was PV over NR over NT equals R, equals that constant. But this is generally the way it's set up. Typically, how we're going to be using this value is we're going to be using this one. Because I'm going to give you most of the values in atmospheres. Liters in Kelvin isn't going to change. Moles isn't going to change. It's just a question of what pressure you use. But the 0.0821 liter atmospheres per Kelvin mole is the one we'll be doing. And you can use that very easily. This is a way with no condition 1 to condition 2. This is just values. Again, this is right out of your book. I have 3 liters of gas, temperature of 300 K. I don't know why they're writing it 3.0 times 10 to the second. It's 300 K. And a pressure of 1.5 atmospheres. How much gas is in there? Well, I've got the values of volume, temperature, and pressure. Didn't change. There we go. And I have my new constant, which is not going to change. All I have to do is punch all those in the PV equals nRT. In this case, I'm looking for N, so I shuffle things around. I take my RT, and I bring it under here. N equals PV over RT. Fill in the numbers. You see how the atmospheres cancel out, the liters cancel out, the kelvins cancel out, and my answer is going to be in moles, which it should be, 0.18 moles. PV equals nRT. If there's any gas law you should know, any gas equation you should know, it's that one. It really helps you through absolutely everything. And that's it. We are done. Hopefully this is going to help you get through the rest of the material for the year and should do well on the test.